Welcome to Module 4, Section 1, and this lesson is about EEG terminology. So here's what we're going to know so far. Brain waves can be used as indicators for specific neurological phenomena such as sleep, motor control, perception, information processing, memory, and abnormal neural function. Neural oscillations are visualized in terms of frequency and measured in units of hertz. And the key questions for this lesson is: what is the International 1020 system? What are 4 possible dimensions that we can obtain from EEG data? And what are some properties of EEG frequency, synchrony, and waveform morphologies? So, EEG electrodes are placed according to the International 1020 system. So this system names each electrode site using 1 or 2 letters to indicate the general brain region. So FP shown here in the front is for the frontal pole, and F in general just means frontal, and C is for central, and then P is for parietal, and O is for occipital, and T is for temporal. So the number indicates the hemisphere. So the odd numbers are on the left and the even numbers are on the right. The number also indicates the distance from the midline. So the larger the numbers, the larger the distance is. So and a lowercase z is used to represent the number 0. So z just means 0, which indicates that the electrode is on the midline. And as mentioned before, EEG signal is multidimensional and it consists of at least 4 dimensions: time, space, frequency, and power and phase. Time is often measured in seconds, and frequency is measured in hertz, which is the number of cycles per second. Power is the strength of the frequency band specific activity, and phase is the timing of the activity. Power and phase are discrete elements of a dimension because they provide largely independent information. So as you can see from this graph, the x-axis indicates time in seconds and the y-axis indicates frequency in hertz. So power is shown in color, where red indicates the strongest frequency band specific activity. And space is another dimension that can be mapped using the International 1020 system electrodes, which you can see here in this bottom figure. So the frequency slice shows power, which is the energy at each frequency band on the y-axis, as a function of frequency in the x-axis. So collapsing over a period of time that could be hundreds of milliseconds to tens of minutes long, but basically time is lost in these plots in the sense that you cannot determine whether and how the frequency characteristics change over time. So these plots are generally useful when no or little time varying changes in the frequency characteristics are expected, such as in a resting state or a sleep stage. In the time slice, one frequency band is selected, and activity at that frequency band is plotted over time. So these plots look a bit like an event-related potential or an ERP, in the sense that you see a line plotted as a function of time. But unlike an ERP, the activity is specific to only one frequency band. These plots are useful for comparing activity across multiple conditions or electrodes, and when you want to focus on a specific frequency band. And in the space slice, the data are shown at one time frequency point, or the average over multiple adjacent time frequency points over electrodes in a topographical plot. So this slice helps us visualize the topographical distribution of the effect and facilitates topographical localization. In the time frequency slice, the data can be shown in a time frequency plot where time is on the x-axis and frequencies on the y-axis. So typically frequencies are plotted such that higher frequencies are towards the top. The picture here is sort of just black and white, but the real image is supposed to have color, which reflects some feature of the time frequency data, such as power, phase clustering, connectivity, or correlation coefficient. Similar looking plots are sometimes used to show very different kinds of results, including ERP images or activity over time and space. So always check the axis labels and legend just to be sure. So EEG frequencies can have different properties, including rhythmic, arrhythmic, and disrhythmic. Rhythmic is EEG activity consisting of waves of approximately constant frequency, and arrhythmic is EEG activity in which no stable rhythms are present. And then disrhythmic are rhythms or patterns or EEG activity that characteristically appears in patient groups and it's rarely seen in healthy subjects. Cerebral dysrhythmia is a disturbance or irregularity in the rhythmic of the brain waves as recorded by EEG. So that's just a side note. And this slide is about synchrony, which refers to the simultaneous appearance of rhythmic or morphologically distinct patterns over different regions of the head, either on the same side or both sides. And asynchrony is the non-coherent occurrence of EEG activities over regions on the same or opposite sides of the head. For instance, two similar waveforms occurring at separate electrodes or channels, but not simultaneously due to a time lag between the channels. And hypersynchrony describes EEG patterns that are attributed to increased synchronization of neuronal activity. So an example of this is hypnagogic hypersynchrony, which involves maximal frontocentral sinusoidal activity occurring at the onset of sleep in normal infants and children. So the shape of a wave or an EEG pattern is determined by the frequencies that combine to make up the waveform and by their phase and voltage relationships. So wave patterns can be described as being monomorphic, polymorphic, or sinusoidal, and transient. Monomorphic waveforms involve distinct EEG activity appearing to be composed of one dominant activity. In contrast, polymorphic waveforms consist of distinct EEG activity composed of multiple frequencies that combine to form a complex waveform. Sinusoidal waveforms have waves resembling like sine waves, and monomorphic activity is often sinusoidal. Lastly, a transient waveform is an isolated wave or pattern that is distinctly different from background activity. So I guess some examples include like spikes, which is a transient with a pointed peak and a duration from 20 to under 70 millisecond, and sharp waves, which is a transient with a pointed peak and duration of 70 to 200 milliseconds. So as a summary, EEG data consists of 4 dimensions: time, space, frequency, and power and phase, and each of these dimensions have several different properties. And in the next lesson, we'll be talking more about the main types of EEG data analysis.